All right, so this is the beginning of our reaction engineering course that I'll be, going over just generally. And so when it comes to reaction engineering, you might be thinking, well, I've spent some time in chemistry lab, or maybe I haven't, but essentially what we think of is I have this flask, this Erlenmeyer, or this volumetric vessel that I'm going to add a little bit of this, a little bit of that, and I'll have some sort of product. So what is up with reaction engineering, right? We're able to make those products and reactions happen in the lab. What is the difference between what we're doing in that lab versus now reaction engineering? And there's a little bit of difference especially when it comes to chemical engineering, because the point of chemical engineering is to take that small scale lab pilot kind of experiment into a large scale version. And so when you go into industry and you want to make a lot of whatever product you want. Let's say you want to make a lot of ammonia, right, through the Haber-Bosch process. Um, those little small scale Erlenmeyers won't work. And so what you have is basically these different kinds of reactors that have been developed, such as batch reactors, CSTRs and PFRs. Looking at this image that I've stolen off the internet, but essentially these are the three main kinds of reactors that we use for these large scale product development. Okay, so now that I've introduced what reaction engineering is, I've just thrown at you a bunch of terms about batch reactors, continuous stirred tank reactors, plug flow reactors. What is the difference, right? Each one is developed for their own specific needs. So if we look at a batch reactor, you can think of it as kind of very similar to what we were thinking of when I was talking about that chemistry lab kind of environment. You dump in a little bit of product reactant A, dump in a little bit of reactant B, and then what you do is you just bottle it up into a vessel, right, into this container, and you have a stir rod in here to make sure that all these species are mixing in properly, right? But essentially, once you've added reactant A and you've added reactant B, right, you're never going to add any more until basically the reaction is done after a certain amount of time. You're not continuously adding any of the reactants. And so this is kind of like something that is used in pharmaceutical industries. If you want to have a product that requires specific limitations or specifications, you want to make sure that you can trace it to a specific batch. And so you'll see this in biomedical engineering sometimes in those cases. A CSTR is very similar, except you have basically a continuous feed. You can see here that it says feed. So what that means is now we have, A, or sorry, wrong color. You're gonna have A and B basically running um, throughout the reaction. And so you're always gonna get a fresh feed coming in, and you're always gonna get product coming out. Now, a PFR is very similar to a CSTR, except you have the feed coming in, and every single like kind of like layer throughout the pipe, right? You're going to have different kinds of concentrations of reactants and products. So you can see that as we continue on down this pipe, you can expect that the concentration, we're going to have more product versus reactants on this end, right? Um, It's very dissimilar from a CSTR, in which basically you can assume that the concentration in this tank is going to be the same as the concentration coming out in the product stream, and so it's kind of a little bit different. And going forward, we'll look into this mathematics of how do we describe these and how that might be different. But for right now, it's important to just understand generally what are the different kinds of reactors, what are their purposes, and get into just basic math on how can we model the concentrations of these reactants and products. All right. So every reactor design, no matter how complicated, comes back to basically one question: how fast is stuff disappearing or appearing? That's it. If you can write down the rate at which a species changes, you can size a reactor, you can predict the conversion, and you can also figure out how long you need to run something. And so today we're going to be building that from the ground up, and by the end you'll understand what differential equation like dCA by dt might mean, and where that comes from. So let's first start with the reaction rate itself. When we write a rate of reaction, it's typically denoted as, let me use red for this. So first thing, right? First thing to know, rate of reaction. And I'll be using RxN for reaction as a shorthand. So rate of reaction is usually denoted as small r, and we're going to denote, let's say that we have some sort of chemical reaction going on, and that's going to be A uh, going to B, right? So it's simple, only one reactant, one product. This is our equation. Not equation, chemical reaction, right? All right. So that's the rate of reaction. So when we write the rate of reaction, little r sub A, what we mean is that the rate at which species A is consumed per unit volume. For a reactant, we usually write R minus R sub A because A is being used up and we want that quantity to be positive. So you can imagine that if we have a reactant over time, that concentration of the reactant is going to go down because we're conservation of mass and we're making more products. We're making more of B, right? We're making more of this guy. And so what that means is that this is going to be a negative value, typically. So we're going to see it as, let me scroll to get this out of the way. Negative. So you'll see it written as minus R sub A. All right, perfect. The key idea is basically that the rate depends on concentration. For a lot of reactions, right, the more A you have, the faster it reacts. And that makes sense, right? If you think about it, if I have, let's say that I have, you know, an environment, right? I have this box. I have this little box, and I have, let's say, only three. Oh, I have, I have only three, molecules of A, versus, right? Versus I have this same size box, right? Same volume, but now I have, you know, instead of three, I have maybe something like this, right? I don't know how many this is, but it's substantially more than what's in this original box. So you can imagine that since I have so many more molecules of A and the same finite volume, that means that the concentration of A is higher, and that means that the likelihood of these molecules coming into contact with one another is greater, right? And that means that there's going to be more reaction going on. So the reaction rate is therefore greater. And so we want to capture this in math, right? So what we can write is that minus RA minus RA is equivalent to KCA, where this is a constant. I'm going to call it the rate constant. And this, as you can imagine, is the concentration of A. All right, perfect. In the reactor. And let me write that. When I say reactor, though, it might also mean in these cases that it's the feed, right? It's not going to be always this because the concentration in the tank is going to be the same in the product. But we'll cross that bridge when we get there. Okay, so K is the rate constant and C sub A is the concentration of A. That K basically carries the temperature dependence through the Arrhenius equation. And so what that means is that this K value, it can often change depending on the temperature. So if you're running the reaction at a higher temperature, this K is going to be greater because, as you imagine, temperature means these molecules are moving faster and faster, right? And so we want to model that. So K is going to be greater. At a lower temperature, K is going to be lower. But for right now, we'll just hold temperature aside for today and treat K as fixed. Let's just say that it's all running at the same temperature. And even if it's fluctuating, it's still going to be the same. All right, perfect. So here is where the biggest part of reaction engineering comes in, and it's the mole balance. So step two, right? And this is basically, let me use purple. So two, the mole balance, right? And so what is this mole balance and why is it so important? In minus out plus generation equals accumulation is basically the hallmark of any chemical engineering class, right? So let me write that down. In minus out plus generation equals accumulation, right? This is the basic principle of mole conservation or mass conservation, however you want to talk about it. This is the modeling in any chemical engineering class, whether it's mass transport or heat transfer or anything. And it's the same case even in reaction engineering. Now, how does that basically translate to reaction engineering? Well, this is where we have that dCA by dt that I was talking about, right? The change in the concentration of species A over time. This is what we care about, right? This, now let me use a different color. Um, this is basically the differential that matters to us. We want to know in any reaction, how is the concentration of the reactants changing over time? Now you might ask, okay, well, why are we worried about the reactants? Why are we not worried about the products, right? After all, isn't the products more important to us? Yes, that's true. But the thing is that the reaction rate, if we look at this rate of reaction, it depends on Ca, right? It depends on the concentration of A in the reactor. So if we want to figure out, okay, how can we speed up this reaction to get more products, we need to have some sort of equation that's going to utilize or tell us how is that concentration changing over time. For any reaction, right, we want to maximize products. That means that we want to do it in the shortest time possible. And so we just want to use the change in time for the concentration, the rate of reaction. All right, perfect. So what is dCA by dt in math, right? dCA by dt is nothing but the rate of reaction. It's equivalent to, here, this is equivalent to R sub A. For the same reasons that I just stated, right? So this basically describes how fast is the species A being depleted, the reactant. And this is going to tell us, okay, well, now that this is the rate, there's a time value in this rate constant. And that should tell us, okay, how is the concentration changing over time. Now let's specialize it to a batch reactor. The batch reactor is the simplest reactor since essentially what we're doing is we're just dumping the reactants into a tank and just letting it sit. And so what that means is in assumptions, um, nothing flows in and nothing flows out. So this in and out term, right? They both go to zero. And so all we're left is generation and accumulation, right? So important to note in batch, no in, no out. In a CSTR and a PFR, we do have, feed coming in and products coming out. But even when we cross that, we're going to have mass balances going on. So shouldn't be a problem. But specifically for batch, we definitely don't have anything coming continuously in or out. At T equals zero, all of our reactants are in that tank, and then they start reacting at T equals zero. And so if we look at generation, what we can say is that generation is R sub A times V because it's the rate of the reaction times the volume, right? We have, let me write that down. So gen equals R sub A times V. It's dependent, right? Degeneration, by the way, is the generation of product that we're talking about here. And accumulation is nothing but d and a by dt. Accumulation by itself implies that something is not steady state, right? Whatever comes in is not coming out. There's some backlog happening that is causing this concentration of not concentration, but the number of moles to increase at some point in that reactor. And so this is why we have a differential going on for the accumulation term. Okay, so now that we have generation and accumulation, let's rewrite this let's rewrite this equation. I'll use green now. So we have R sub A times V is equivalent to D and A by dt. All right. So how do we take this equation and convert it to dCA by dt equals Ra, right? We don't care right now about the number of moles. What we want is concentration. And why do we want concentration? Well, it's because we know that a rate of reaction is written in terms of concentration. We want to get this term involved. And so we have to convert this differential into this. All right, perfect. So one thing that's really important to note here is the definition of concentration. So what is concentration, right? Concentration is the amount of moles that we have of A divided by the volume, right? So if we take this, we can easily convert this differential into dCA by dt simply by dividing both sides by volume, right? So if we divide both if we divide both sides by volume, we get R sub A is equivalent to dCA by dt, right? And that is exactly what we have up here, right? All stemming from basic definitions from a batch reactor perspective, obviously, but you can apply for other reactors. The generation is basically the rate of reaction times the volume. The accumulation is how much of moles of A is changing over time. And if we assume that the volume is fixed, or actually it doesn't even matter because this is the definition of concentration, we can convert this equation into the general equation that matters is dCA by dt equals Ra. All right, perfect. So now that we've basically derived this, we can take this a step further. Now that we know that Ra is, little r sub a is negative kCa, we can also rewrite this as dCA by dt is equivalent to minus kCa. And so this is our ODE that we can use to then get an equation for how is the concentration changing over time. So just as a quick kind of derivation, I can derive for a first order reaction, I can derive the equation. So let's say that we have a first order chemical equation, a reaction going on like what we had here, A going to B. If I was to say, um, find how concentration of A changes with time, how would we do that, right? Well, when it comes to differential equations, you know that you would always need a kind of an initial condition, especially when it's time is the variable that's being relevant here. So let's say that we have an initial condition, right? Or IC is that at time equals 0, the concentration of A is equivalent to Ca naught, right? So now that we have our initial condition, and this is a first order, constant coefficient ODE, this is simple to solve. So now let's solve it. So dCA by dt is equivalent to negative kCa. All right, now I'll switch over. So then we have basically multiply both sides by dt, divide by Ca. So we get dCA CA is equivalent to minus K dt. And so we have dCA, we have differential on both sides, dt on this side. What do? Integrate. Take the integral of both sides. The integral of 1 over CA is nothing but ln, natural log of CA. And this is a constant, so we can pull it out of the integral. So you get minus K. The integral of 1, there's a 1 in here that you can multiply by. The integral of that is nothing but the variable itself. So minus kt, and always remember to include your constant, right? All right. Now we have to solve this for CA. So CA is equivalent to e to the minus kt plus c. We can now plug in our initial condition here where t equals 0, CA equals CA naught. So plug C. If we plug in 0 for this, we get nothing but e to the c, which is a constant, is equivalent to CA naught, right? Because this is CA naught equals e to the minus 0 plus c. So we can call this constant e to the c. Let's just call e to the c as CA naught. So if I was to rewrite the equation now, we get CA is equivalent to CA naught plus e to the minus KT. Sorry, not plus. Multiplied. CA naught times e to the minus KT. Yeah, so this is now the equation that tells us how is the concentration of A changing in the reactor with respect to time. And this is for a first order reaction, but depending on, what your specific reaction is, if it's second order, or third order, or even for negative orders, and so on, you can solve this equation for that too, as long as you know what R sub A is, right? So when it comes to second order or third order reactions, this R sub A is going to change. That's what's going to fluctuate. And so it's just a matter of then plugging in what R sub A is into this equation, right? Into this one, and then just solving for the concentration. So I think it's an important note is that this is only for first order reactions. But this is the general uh, this is the general form. Oh, what's going on here? All right, hopefully it's all right, perfect. General form. Is there anything else I wanted to add? I don't believe so. So I think I'll end on this note, and then we can, in the next video, I can go into specifics on batch reactors, and we can talk about, okay, well, what happens, because in industry, what happens is that we don't always have one batch reactor, right? You probably have chains, and we'll talk about why we might want to do that when it comes to conversion. So conversion and yield is something that we can talk about for the next video. But this is the general format of how do we determine the concentration of a certain species when it comes to time, right? Just to reiterate, what we do is that we figure out what the order of the reaction is, right? R sub A. It's usually going to be negative because you're going to have depletion of the reactants. Once you have R sub A, you have this equation dCA by dt equals R sub A. In the batch reactor, you have no in and no out. So this is the general form for a batch reactor that's going to work with a mole balance. When it comes to CSTRs and PFRs, we're going to have different mole balances that I'll talk about. And then once you have that, once you have R sub A and you have dCA by dt, you just plug that in, integrate, and use your initial condition in order to get the final equation. And I'll catch you in the next one.